Hi, everybody. We have some fascinating applications of vector spaces. We'll start with the differential equations. So linear, now this, what I'm saying now applies to linear differential equations. Don't forget, because this is linear algebra. We're going to see a lot of a lot of interplay. I don't know what the word is, intersection. I don't know how to say it. But a linear differential equation is y to the n plus some function of x times y to the n minus 1 plus dot, dot, dot. Now, just to say, I say this whenever I teach differential equations. The g functions, the functions g of x, they may or may not be linear functions. That's not what makes this a linear differential equation. What makes it a linear differential equation is if you don't have like a y squared or a y prime times y or anything like that. So when we say linear, we're talking about the y things are linear, sort of. Nothing's getting squared, nothing's getting square rooted, anything like that for y. Anyway, we talk about them being homogeneous and non-homogeneous, whether this f of x here is equal to 0 or not. And of course, you notice that terminology, homogeneous and non-homogeneous, is like, it's the same way we said homogeneous, non-homogeneous in linear algebra. So there's a lot of interplay. But again, it's not that linear algebra and differential equations are so connected per se. It's that linear differential equations and linear algebra are very connected. That's in the manner that we're about to talk about. Anyways, when we have functions, we mentioned that functions can be viewed as vectors. So, for example, if I have a linear differential equation, y double prime minus y equals 0, I can get two solutions, e to the x, e to the negative x. These two solutions are linearly independent. In other words, if you view these guys as vectors, they are linearly independent vectors. And really, in differential equations, what we call the general solution is really a linear combination of these two linearly independent vectors. See, if you take a course in differential equations, they may or may not present it in that way, but that's the reality. So whenever you have something like this, the general solution y is equal to some constant times e to the x plus another constant times e to the negative x, you can consider e to the x and e to the negative x as two linearly independent vectors in a vector space. The vector space here of vector space of twice differentiable functions. Actually, I'm actually going to highlight that. That deserves highlighting. Yeah, let's highlight it. That definitely deserves highlighting. What if I can highlight this thing also here? That'll be cute. One less thing I gotta highlight. Oops, just trying to highlight one less thing. Come on. Oh, that's not what I wanted. Boy, this highlighting thing is becoming the highlight of my life. Anyway, anyways, I don't know why I can't. Oh, here we go. Yay! Finally. What is that? Boy, this is a big waste of time. So let me pause. So the vector space of all twice differentiable functions, that's the vector space, and y equals e to the x and y equals e to the negative x are linearly independent, and it all fits into what we do. So basically, the general solution is really the linear combinations. We never, when you take, as I said, that may or may not be presented that way in a differential equations course, but that's really what we got here for a linear differential equation. Anyways, let's look at a very important, very, very important theorem, which again, you may have come across in your career, that the solutions of a linear homogeneous differential equations. So here's my linear homogeneous differential equation, and my solutions. So it's a theorem that you may or may not have learned if you ever took differential equations. That an nth order linear homogeneous differential equation has n linearly independent solutions. And if y1, y2, yn is a set of linearly independent solutions, then every solution is of the form c1, y1 plus c2, y2, dot, 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 plus cn, yn, where the c's are all real numbers. And this is how linear differential equations are done. But hold the fort here. if you're solving a differential equation, an nth order linear differential homogeneous differential equation, and you get a bunch of solutions, it really is in your best interest to know for a fact whether these solutions you got are linearly independent to each other. Because if I have a fifth order linear differential equation and I homogeneous and I get five different solutions, I want to make sure that they're all linearly independent, because if they're not, then there must be more solutions out there, so I know I solved them all if they're linearly independent. So it would be awesome if there was some way we could figure out, if we could test whether a bunch of solutions are linearly independent. Funny you should mention that. That's where a concept called the Wronskian comes in. Now, first I want to just define what Wronskians are, then I'll get to the point of how we use this for differential equations. If you have a set of functions, y1 through yn, and just a bunch of functions, and each of which has at least n-1 derivatives in some interval. So the Wronskian of these functions is the determinant equals the determinant of this sucker right here. So on top I have y1, y2, dot, dot, dot to yn. Now in the second row I have y1 prime, y2 prime, yn prime, dot, 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 all the way down to like the third row. The next row will be y double prime, y2 double prime, yn double prime, so on and so forth, until I get down to the n-1th derivative. And you know how far to go, especially when you see, the matrix finally becomes a square matrix. So just to give you an example of finding a Wronskian, here's two quick examples. If I have a set 1 minus x, 1 plus x, and 2 minus x, so the Wronskian, so on top I put 1 minus x, 1 plus x, 2 minus x. The derivative of this is -1. The derivative of that is 0. 1 plus x, the derivative is 1. The derivative of that is 0. And again, we have 2 minus x, -1, and a 0. Well, this bottom row is all zeros. So so we know that when that happens, the determinant is equal to 0, and there we go right there. That's our 0. And now we have x squared, x cubed. We want to see if these are linear. We want to take the Wronskian of these three functions. Again, how we're going to use this for differential equations, we're going to see in a minute. So the derivative of x is 1, the derivative of 1 is 0. X squared, the derivative of x squared is 2x, which has a derivative of 2. X cubed, 3x squared, 6x. And now if I take the determinant, and I'd like you all to do this on your own as an exercise, you will see that the final answer is 2x cubed. Now, answer for number A, we say that the Wronskian is identically equal to 0. It means no matter what x is, for all values of x, the determinant is always 0, because it's just the constant 0, so it doesn't matter what x is. Whereas the second one could be 0 if x happens to equal 0, but there's quite a few other values of x which will make this non-zero. In fact, there's infinitely many values will make it non-zero. Now, why am I pointing out this idea of identically equal to 0? Funny you should ask. And that is because we now have the Wronskian test. Now, the Wronskian test tells us that if I have a bunch of functions, n functions, which are all solutions of an nth order linear homogeneous differential equation, this set is linearly independent if and only if the Wronskian is not identically equal to 0, which means these guys, in the example that we just did, these three functions are not linearly independent, and it's not that hard to see how you could make that happen. And these three are linearly independent because this is not identically equal to 0. Yes, it's possible that 2x cubed could equal 0, but it's not always equal to 0. Whereas this is, 0 is always 0. So these three functions are not linearly independent. These three are, according to the Wronskian test. I just want to point out that when we defined the Wronskian test, we just took n random functions. But I'm sorry, when we defined when we defined just the definition of the Wronskian of a set of functions, So that's defined for just any n random functions. But when we talk about the Wronskian test for linear independence, we can't just take n random functions. It has to be n solutions of an nth-order linear homogeneous differential equation. Otherwise, the test has no validity. So that's important to realize that distinction. So if I have a bunch of functions, a particular linear homogeneous differential equation, and I want to know, are these n solutions linearly independent, do the Wronskian, and then if I discover that they're not independent, I know I have to start searching for some more solutions because I know that there are going to be n. Anyway, get it. So let's look at some examples. Let's look at the differential equation y triple prime plus y prime equals 0, and we want to know if now we know we're telling us if you want to know how to solve this differential equation, take a differential equations course. But if you would solve it, you would get 1 cosine x and sine x. And if you take the Wronskian of these three functions, 1, 0, 0, these are all the derivatives. If you take this out, you wind up getting. By the way, I would definitely do this determinant on the first column because you have all 0, 0. Anyway, you wind up getting sine squared plus cosine squared, which is equal to 1, which is actually never 0 because it's a constant 1, so it's never going to be 0. That means that 1 cosine x and sine x are indeed linearly independent, and they would be your three solutions of your three linearly independent solutions of the original differential equation y cubed plus y prime equals 0. Yay. And if you want to test a set of solutions for linear independence, let's do another test. So we have x triple prime minus 3x double prime plus y double prime, sorry about that, y triple prime plus minus 3y double prime plus 3y prime minus y equals 0. And we want to, now, again, this is not a differential equations course. So I'm just going to tell you this, three solutions are e to the x e to the x, and now x plus 1 e to the x. Now, the question is, are these linearly independent or not? And so we're going to do the Wronskian test. You could actually look at this and kind of figure it out a little bit, but because the truth is, if I actually add the first guy plus the second guy, I get the third guy. So I know the answer is going to be no, but let's see what the Wronskian tells us. Well, if you do the Wronskian and take this determinant, again, here's the three functions I'm laying across the top. I take all the three derivatives, and then I do the determinant. It's a crunch it. You wind up getting 0. So clearly, these are dependent, not independent. And that's something we were even able to see just on inspection. But the point is that this test works. The Wronskian test works. Okay, moving on. Well, that's the end of Wronskian. It's a fascinating, fabulous topic, and we're going to make another video about another tremendous application, and that's coming up next. So, bye everybody. We'll see you when we see you. How you like that?